Okay, hi everyone. So I'm gonna have a look at the questions of the week 6, workshop number 5, and we can proceed with the question 1. So we see that here, uh, the question is about whether there is a Eulerian cycle or Hamiltonian cycle in any of these graphs or not. So we see that the degree of this vertex is just 1, the degree of this one is just 3. So for having Eulerian cycle, we should have all of the vertices degrees should be even number. So this one is not Eulerian cycle, and also this is not Hamiltonian cycle, because in any condition, if we start here, we will touch this server in order to get this PC1. We will have to touch it like twice. Now, for the second one, we see that obviously it's not Eulerian cycle because this degree is 3. For Hamiltonian cycle, we see that this is just Hamiltonian and it is easy to see. And this guy here, the degree of this one is 3, so it's not an Eulerian cycle. Okay, it doesn't have Eulerian cycle, but it is Hamiltonian for sure. So we see that we can have a cycle and we can touch or pass from every vertex just one time. So question 2 is about the Eulerian and Hamiltonian path, not a cycle. Now we see that this guy has degree 1 and this guy is 3. So this, if we start from server, we go to Mac1, Mac2, server, and PC1. And we have used all edges just one time, and we covered all the vertices. So it's Eulerian path. For having Eulerian path, in fact, we should have only 2 odd degrees. Okay, the same thing happening here, because we have 2 odd degree vertices, this guy and this guy. And the same thing is happening here. This one, 3, and this one is 5. 1, 2, 3. For the loop one, we counted 2. All right. So for Hamiltonian path, those ones having a Hamiltonian cycle, we can count it like, therefore there is Hamiltonian path. Okay, for sure. Starting from here and getting here, and for example, and having all the vertices covered. Okay. Now, for question 2, also we can talk about this guy as well. Hamiltonian one. So this one is Hamiltonian as well. We see that. So all edges have been covered, and we passed all vertices just one time. So it's Hamiltonian as well. Now, let's go to the question 3. So we see that, recall that a cut point is a vertex such that if it is an incident edges were removed from the graph will cause the graph be a disconnected one. A Hamiltonian graph should not have a cut point. So why not? So let's have a see. So I'm gonna write it here. So for example, this guy, this guy, this guy. So obviously the one in the middle is the this guy is the cut point. So this is not a Hamiltonian one, because if I start from here, then if I pass from here, so in some at in some case, I should come back from this vertex again to get where I started. So it will be impossible because I have to touch this vertex again. So this this counter example say that the Hamiltonian graph cannot have any cut point. So counter example for the claim that a Hamiltonian can have a every Hamiltonian cycle have a cut vertex, but no, it's not like that. So a Hamiltonian cycle cannot have for obvious reason. And one example, which is not a proof, but it supports the idea that to say a Hamiltonian cycle graph, a graph which has got a Hamiltonian cycle, it cannot have a cut point. Now, let's have a look at the question 4. So question 4, so it's about the famous theorem. Dirac's theorem says that if G is a simple graph with n with vertices like more than 3 vertices, and if every vertex has degree like n over 2, so for 3 vertices, 3 over 2 is 1.5. So every vertex should have 2 degree. Then G has a Hamiltonian cycle for sure. So let's see one example. So one of the famous example is like this one. And we see that this is like find a graph with 5 or more vertices. So it's easy to see that if we start from here, we go here, here, then here, and then here. And this means and we see also that the degree of this one is 2, okay? And the degree of this one is 3, and this one is 2. This one is 4. So the question says find any graph on 5 or more vertices that satisfy the conditions of this theorem and illustrates that the theorem is true for your example. Okay, so this is 5, 1, 2, 3, 4, 5. So 5 vertices, and we have 5 over 2. So 2.5. So one of that, this one is 2. So this, so not having this assumption doesn't mean that we cannot have a Hamiltonian cycle. So I just, this example shows that this condition is not like necessary condition, but it's enough condition. So the other example which comes to my mind is this one. So maybe this one. So this guy, this guy, this guy, this guy. So if I start from here, 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 and here. So this is like 6 of them. So 6 vertices, and most of the vertices are like at least 3 degree 3. So we have a cycle, Hamiltonian cycle. The other one is K5, just comes to my mind. So this guy, this guy, this guy, this guy, and this one. So definitely Okay, this is the Hamiltonian cycle. We use just every vertex just one time. And the degree of the every vertex is 1, 2, 3, 4. It's just 4, which is more than 5/2. Okay, these are the example about the Dirac's theorem. All right, so now we go to this question now. Now, here's the weighted graph, and the adjacency matrix is given here. So you see that, so I can label them. Then after I've got this one, A to A, which is 1, A to B, which is 2, A to C, which is 3, B to C, this is 3, this is C, and B to C is this one or this one. B to C or C to B is 4. Okay, and the weights on each edge has written on there. Question 6, let's have a look at this interesting types of the graphs. And we see that here it's not a graph, so this one is about the famous traveling salesman problem. Okay, and as the for minimum weight of this one, so minimum weight of the Hamiltonian cycle, so the traveler will meet every house or vertex, and he or she wants the minimum of the effort. Okay, so from here we see that let's have a look at the questions. Find all the Hamiltonian cycle on the complete graph K4 with vertices A, B, C, D, A, B, C, D. It's like this. In this context, cycle using the same edges are considered the same. A, B, C, D, A, B, C, D, the same as B, C, D, B, C, D, A, B. So obviously, so because the summation of the degrees will be the same. And hence, let's solve the traveling salesman problem on the weighted K4 as specified by its adjacency matrix. Okay, so this is this guy and this is this guy. So we will have 3 Hamiltonian cycle for this. So the one is like, as it's written, starting from here, A, B, D. All right, sorry. This one, this one, this one, which is 4, 1, 4, 5. So the summation is 4 plus 1 plus 4 plus 5 is 14. Now the other one is, so let's call this one A, B, D, C. The other one is A. So let's say D. Then maybe I can go here. B. Then I can come here. Then I come back here. So 3, 1. Then this one, 2, then this one, 5. So this will be 3 plus 1 plus 2 plus 5. So which will be 11. So the other one is definitely this one. So AB, what's that? 4. This one is 2. So then I came here 4. And then this one is, which is 3. A, B, C, C, D. This is A, so the D for this one is 4 plus 2 plus 3 and plus 4, which is 9 plus 4 is 13. Okay, so which one is the minimum? So obviously this choice of the edges are the best one because it has minimum expenditure. All right, let's do another question now. So the interesting graph is like this one that I made in the previous question. N cube Qn is a graph isomorphic to G defined as follows. The vertices are all possible binary strings. So the name of the vertices will be like it will be coded or labeled by binary strings, and the length of the binary strings will depend on the number of the vertices. So if we have 5 vertices, each binary has like each vertex has a binary which the length of the binary or the number of 0 ones are 5 of them. So here is the vertices, n vertices, and each vertex has got 0, 1, 0, 1, 0 like this. There is an edge between any two vertices if and only if vertex strings differ exactly one in exactly one position, one place. For example, this is the same as your the one that you have seen in your assignment. So this one, you see that here. So only one is differed with this, the first string vertex is an edge. There is an edge between them, okay? But there is not edge between these two vertices, okay? 0, 0 is the same, 0 and 1. One difference, 1 and this 0, it is the second difference. So we should have only one difference, exactly 1. So there is not edge between them. Now, here is the question 7, part A. So I will have n equal 1. So my string will be just 0 or 1. So 0, 1. Okay. And also, I believe that this one here, sorry, this one here should be a sub 2 power n actually. Okay. So this one is the name of this edge is vertex is 1. This one is 1. So I'm talking about this n equal 1, and we have 0 and 1. For n equal 2, you see that we've got, let's first see that how many vertices do we have. According to the thing that I wrote here, we see that it should be 2 power 2 for vertices. Okay. And they are 0, 0, 0, 1, 1, 0, 1, 1. So actually, let's have this one here. So let's make a space. You see that 0, 1, 1 difference. So there is one difference, just this one and this one here. So we draw edge. We draw an edge between them. This one also qualified for an edge between them. This one is also, and this one is also, and this one is also no. It's just because 0, 0, and 1, 1, they are two different. Now let's have a look at the complicated one, n equal 3. So the number of the edges, vertices actually, should be 2 power 3 is 8. So we will have 0, 0, 0, and this can be to be with this 0, 1, 0, and also maybe 0, 1, 0, and maybe with this 1, 0, 0. There won't be any edge between them, so should and also, so this, there will be, okay, 0, 1, 1. What else I have? There is edge between this one as well. Okay, there should be another thing here, maybe 11, 0. There is another one between this one and this one. There should be here something here as well. So okay, let's do this one, 1, 1, 1. Okay, so there should be an edge between this one. There should be another vertex. What's that? One, 0, 1. Yeah, and there is edge between this. There is edge between this. Yeah, we are done, I think. Yeah. So yeah, this is the edge. So I should. So actually, this one, this is a cube, and this is for this n equal 3, and this is actually q sub 3. All right. So about the first one is like find the Hamiltonian cycle for this one, and if your method generalized to higher end, you may have found something very useful. So it seems that gray code, you can find it here, and you can find how to draw the q sub ends. So the Hamiltonian one should be this one. Can I draw this one? I hope 0 from here. Let's go from here to here. Then let's go here. Then let's go to 100. Then let's go to 11, 0. Then probably we can go maybe here or here. So let's make it complicated here. Then we can go here, 0, 11. And then we can go here. And then we can come back to the home. Awesome. We finished with this one. And this is the Hamiltonian cycle.